This video lesson is on something called colligative properties. A colligative property is a property dependent on the concentration of the solution. So basically, when the concentration changes, the property changes as well. Some different properties of solutions include not only the concentration, but also the melting point, the freezing point, the viscosity, or how easily it flows, and also something called vapor pressure. The two that we're going to talk about most are boiling point and freezing point. When a solution changes its concentration, its boiling point and freezing point also change, compared to what they would be if the solvent were pure or had nothing dissolved in it. Viscosity is something that exhibits colligative properties, but it's not something I'm willing to talk about in this class. The two colligative properties that we're going to talk about are boiling point elevation and freezing point depression. Now take, for example, a pure solvent like water. If a solution is 100% water, water boils at 100 degrees Celsius. But as soon as you start adding solute to the water is no longer pure, but the solution that contains mostly water actually boils at a temperature greater than 100 degrees Celsius. In other words, it elevates the boiling point higher than it would be if it were in its pure solvent state. As a result, the solution needs more energy to boil and requires higher temperature. Now, a common misconception is that adding salt or sugar or any solute to water makes the water boil faster. A lot of you will talk about or bring up the idea that adding salt to water when you're making your macaroni and cheese or your spaghetti makes the water boil faster. No, it makes the water boil hotter, not faster. And because the water boils hotter, the food cooks faster. But the actual time it takes for the water to boil from put into the pot to boiling is actually slower because it takes higher temperatures to reach boiling. Now let's contrast that with freezing point depression. The same concept. Freezing point goes down compared to what it would be in its pure state when you add solute to the solvent. So if water freezes at 0 degrees Celsius, then a solution would freeze at a temperature lower than 0 degrees Celsius. So in other words, a solution might be about maybe -5 degrees Celsius. Now what's cool is that the more solute you dissolve in the solution's colligative properties continue to go down, down, down for freezing point depression, or continue to go up, up, up for boiling point elevation. Going back to the last slide, the colligative property exhibits the property stronger than it would be, and the more concentrated, the stronger the property is represented. You might be asking yourself, why does dissolving solute into solvent actually change anything about the boiling point or freezing point? And the answer is down on the molecular level. Now when water boils, it gets heated up, and then the heat causes the particles to wiggle and move faster, and so eventually the heat is so high that the particles break their intermolecular forces between each other and escape as vapor. Now let's remove the intermolecular force between water molecules and actually add a positive ion to the solution, and what happens is the water no longer is attracted to itself, but rather the positive ion is attracted to the negative side of the water molecule and actually forms not only dipole-dipole interactions between water molecules, but also these ion-dipole interactions between the ion itself and the dipole of each molecule. Now it's basically more bonds that water can make, not only with other water molecules, but also a new ion. And the more bonds means more energy needed to break those bonds in order to achieve the necessary energy to escape as a vapor or boil. So the more bonds, the more intermolecular forces there are by adding a solute to a solution, the more bonds, the higher the temperature it needs for that to boil. Now let's take the same concept, but rather think about it in terms of freezing. Two water molecules, once again, without the presence of any solute dissolved in, the water molecules, as the temperature goes down, the particles slow down and slow down and slow down, and eventually they slow down and move less and less, and then eventually they go from liquid to solid. They form a solid state of matter by having attractive forces between the two particles. Now once again, we'll get rid of the particle, or the intermolecular force between, and actually put a sodium in between the water molecules. Now the water is cooling down and cooling down and cooling down, and they're trying to freeze, but this pesky sodium is in the way. It's physically blocking these two water molecules from forming that bond between one another to form an ice crystal. It's like a wall between the two water molecules. As a result, we need to lower the temperature colder and colder and colder in order for the ice particles to begin to create out of liquid. So we need to lower the temperature in order to make ice formation compared to if it were just pure water. This particular property of freezing point depression is especially useful for us in Minnesota. In the wintertime, the temperatures outside are very cold and water will freeze to ice very, very quickly. But as Minnesotans, we throw salt, NaCl, onto our driveways, sidewalks, and roads, which then actually dissolve into the ice and lower the freezing point at which the ice can become solid. So rather than water freezing at 0 degrees Celsius, it freezes at -5, -10 degrees Celsius. So the air outside could be cold enough to freeze, but because it's mixed with ice and salt together, the freezing point / melting point is lower than the air temperature, and so the substance, the solution, stays a liquid even at cold temperatures. You can also base this observation off the heat curve. If I draw a heat curve quickly using just a basic sketch, if this is the normal boiling point of 100 and normal freezing point for water, and now I add in salt to the water, and what happens to the boiling point is instead of boiling at 100, it boils at maybe 105 or 110. Remember, the more I dissolve, the higher it boils. The same is true for freezing point. The more I dissolve, the lower it freezes. So I can draw a green line above the boiling point and below the freezing point. And if you zoom in on this particular spot right here, the difference between the normal boiling point at 100 and the new boiling point at maybe 105, this change in temperature is the boiling point elevation. It's the change that it occurs when the solute is dissolved. The green line is higher than the normal boiling point. Now I could do the same thing down here on the other end. I can think of the black line as the normal freezing point of water, which is 0 degrees Celsius, and then this is maybe -5 degrees Celsius, and this freezing point depresses below. So the green line represents the depressed freezing point or the elevated boiling point. And I zoom back out so you can see that. So there will be one question on the test, at least, dealing with colligative properties, and it'll basically be revolving around this concept of the heat curve. Solute gets dissolved in solvent, the boiling point goes up and the freezing point gets down. Or in other words, 0 and 100 get wider apart. Freezing gets colder, boiling gets hotter. The final practical application of colligative properties is shown on this picture. This is a picture of the side of an antifreeze / coolant bottle. Now, not many of you do work on your own cars anymore, but those of you who do know that you add a liquid to the radiator in order to protect it against extreme temperature changes. Now, the reason you do that is because you're making a solution out of water and what is known as antifreeze or coolant. This happens to be maybe something like Prestone or something like that. Now, these antifreeze / coolants are what are known as ethylene glycol. So if you actually tasted antifreeze and coolant, and I wouldn't recommend it because it's very dangerous and very poisonous, but it actually has a sweet taste to it, which is why you don't leave antifreeze out, because animals don't know the difference. They take one lick, it's sweet, they keep going, drink it all up, and they definitely would poison themselves and die. But you would add it to a radiator, which could protect the temperature ranges. If you look here, if you mix 50% Prestone and water, what you'll get is a protection of high temperatures. So normal temperature water boils at 212 degrees Fahrenheit, so you get 55 extra degrees of protection on the high end, and normal water freezes at 0 degrees, and 32 degrees Fahrenheit, so you get 32 minus 34, So you get like 66 degrees of temperature protection on the low end. By mixing Prestone or antifreeze with your water in your radiator, you can protect your radiator from freezing/boiling, which would cause it to explode. That takes care of this video lesson. Thanks for listening.